So welcome everyone to this event celebrating 20 years of xAct tensor computer algebra. So my name is Jose Martin-Garcia. I am the original developer of the first packages of xAct. And now I work at Wolfram Research here in Urbana-Champaign in Illinois in the US. I want to start by thanking my colleagues at Wolfram U for helping organizing this event. I appreciate your help. And before moving on, in case there are some attendees who do not know already or yet what xAct is, let me make a 1-minute introduction to xAct. So xAct is a collection of packages for tensor computer algebra, and it's mostly focused on general relativity, but it has been used in many other areas in high energy physics or many other areas of physics or mathematics. You can download xAct from its webpage, which is this webpage, xact.es. There is a tarball here with many of the packages for Linux and Mac or for Windows. And for other packages, currently there are like 23, you can go to their respective web pages in GitHub or other places. Here you also have lots of documentation. In particular, the two main files to look at will be xTensor doc and xCOBA doc. And there are also videos. So I recommend you to go to the videos listed here. In particular, one of the last ones, introductory videos, is this one here in YouTube. And I also invite you to look at this page, which lists the packages we are aware of, the articles we are aware of using xAct. And so you get quickly an idea of the variety of topics that can be addressed with xAct. There are also PhD and master theses at the very end. And some of these have full appendices with xAct code. So they are also very good introductions to what can be done. And finally, another page I wanted to mention here is the page of versions. So this is a collection of versions of xAct, and you see that the first one that was publicly released was version 0.7 in March of 2004. So that's the event that we are celebrating 20 years of today, the release of the first public version of xAct. And you see that we started with 0.7, and I have here this file, which is the history file of xTensor, where you can see what happened before, just in case you haven't seen this before. So let's see. So the first public version was released, as I said, in March of 2004. But before you saw, you can see what happened in other versions. And for example, if we go to the very beginning, we see that the original name of the project was mTensor. Then it was changed at some point to xTensor with an E. And then sometime later, it was changed to xTensor with an X. And then another package called xPerm was separated. And then a new name had to be invented for the whole project. And that's where the name xAct came, with ACT being the initials of tensor computer algebra. So that's a bit of the story of what happened here. And yeah, so the first public version was in 2004. And since then, we have had many other versions as listed here. And that's what we are celebrating. Okay, one more minute explaining what we will do today. So today, we have the pleasure of having 6 of the most powerful developers and users of xAct. And they helped me a lot in the first years of xAct, both shaping the system and showing how powerful it was. And so I'm very thankful for all of them for presenting their work today. And what we will do is to have these 6 short talks. So these times are approximate. The idea is to have talks of about 20 minutes. Then after each talk, we will have plenty of time for questions about those talks, or you can also post questions in the big marker form for questions. If they are about the talk, the speaker will address them after the talk. If they are about xAct in general, perhaps the rest of us can respond during the presentations. What else? Yes, so there are a few polls where we ask general questions, and also we ask for those of you who have already used xAct, I'm asking some questions about whether you want to have information messages, both when loading packages and when defining tensors and manifolds and other things. So I've seen many of you removing those messages. So I'm just wondering whether we should just by default remove those messages. So cast your votes, and then near the end, we will look at the results and discuss what to do. Okay, I think that's all from me. So I'm going to stop sharing and let Juan Antonio Valiente Kroon talk about conformal studies of spacetimes with xAct. Thank you all, and I hope you enjoy our event today.
It's a pleasure to tell you a bit of what I do with xAct. So I have this fancy name of Conformal Explorations of Spacetime with xAct. And so what I want to describe is not really a package, but I guess the way you could use xAct in a big, large-scale project. And the large project I want to tell you about is the following. So some years ago, 8 years ago, I published a book. You can see this, so some sort of advertisement here. So this book is Conformal Method of in General Relativity. So some of the people who hang around with me know what this is about, but this is new for you. So this book goes about certain equations called the conformal Einstein field equations. So these equations are a conformal representation of the Einstein field equations, which allows you to study global problems, so existence and stability, and also study of asymptotics using a compact manifold, so using Penrose's idea of conformal compactification. Okay, so if you go through this book, then there are, so describe some of the main milestones in the field, right? So some of these, which I have summarized here, but this is not really just to give you a taster, is the global stability of the Sitter spacetime, semi-global stability of the Minkowski spacetime, construction of the ADS spacetimes, for example, in string theory, and also the analysis of partial infinity, right? So these results are not original of myself, right? But then now this book, what it does is it gives you a unified view of all these results and collecting results from this. It's more like a literature overview. Okay, of course, right, to write this book, I have to go through a huge amount of literature, and somehow that happens. I did most of the calculations of this book by hand. So also, mind you, this is a book which is around 600 pages. And after I finished the book, so I already, so as I said, this book was published in 2016, and I was already, I would say, an expert user of xAct at the time, but somehow, because of time constraints, I just decided that the simplest way to keep this book and finish this on time was doing it by hand. But I think I was wrong. So after I finished the book, I then realized that actually it would be very nice to actually have a companion, a computer algebra companion of this book. And I have spent some years afterwards trying to do that precisely. And so why you wonder why? So why we really need to have, so you have this book, why you need to have an exact version of this? Well, so first of all, obviously, as I said, so all the calculations were done by hand. Of course, most of the calculations were in the literature, but then, of course, conventions and notation and so changes. And so it's actually, if you really want to use this book to make it be useful, really you have to be sure that the correctness of the equations, right? And if you do it by hand, well, there is always this question, right? The other thing that happens is that, there are a lot of formalisms being used in this book, right? So there are many tools, which I will talk about a bit more later on. So like metric formulation of the equations, frame formulation, spinors, and so on. And then you want to compare things in an easy way, right? And as you will see also, so some of the mathematical arguments, although there are some theorems that use abstract arguments from PDEs, nevertheless, to make use of these PDE techniques, you also need to do some involved calculations. And this is an invitation to do computer algebra, right? And then, of course, I think the book is intended to be as a starting point to develop the area further, right? And then, of course, you may think, look at a theorem or a technique in the book, and then you would like to extend this, right? Then I think nowadays the best way is to do that with computer algebra. You may also think that this is, you may want to implement numerically some of the equations. Then again, I think even in numerical applications, it's even more important to be able to to be sure that your equations are correct. So then of course, again, having a exact version of this is essential. And then something, for example, that is also very relevant for my own research, so doing asymptotic expansions. And then xAct is a very natural starting point to do this sort of approximate methods. Okay, so as I said, so the book is 600 pages, and then there are a lot of involved mathematical arguments, but there is, I think, a common thread. And of course, also, what sort of things you would like to do in xAct? Well, so one of them is to derive key equations. Then the other thing is that you want to apply methods of partial differential equations. And then, so applying this methods of partial differential equations requires often to bring these equations that you have derived to a certain standard form where you recognize that equations are hyperbolic or elliptic. And then again, the computer algebra or xAct is ideal for this. So then, as well, so also some of you who know about the sort of questions on initial value problems, so there is the propagation of the constraints, right? So when you do an hyperbolic reduction, you have to drop certain equations, and then you have to verify that the evolution equations preserve these constraints. And this is somehow tied as well with the integrability condition. So this requires a huge amount of tensorial or spinorial calculations, which, again, not naturally done with xAct. Yes. So these are examples of sort of things you would like to do. Okay, and also I guess a disclaimer. So I have learned quite a lot. Well, quite a lot. In fact, everything I have learned from xAct is through interaction with and collaboration with Alfonso Garcia-Parrado and Thomas Backdahl, right? So who have taught me everything I know basically on xAct. And so as you will see, so I will show you somehow an idea of this implementation of my book in xAct. And so this requires quite a lot of packages, right? So in particular, I'm using xTensor, of course, so TexAct to extract equations and put them in a nice way in LaTeX, xCOBA for component calculations, SymManipulator, and also the package Spinor. So there are really essential tools for what I'm going to show to you now, right? So then with this, then I move into my the notebook I want to show. And so this is the implementation of the conformal length field equations. And then also I think some credits. So this is actually, I think, built on a very early version of a notebook that Alfonso did. And he brought to my attention that you could actually do what I'm going to show you. So just to give you some historical context, so it's probably more than 12 years ago. So I gave some course on the subject of this book. And then so Alfonso was one of the attendees of this course. And then I discovered that every afternoon after I was doing the presentation of this course, so it was, I think, a couple of weeks, Alfonso was going and doing implementation of deriving the equations with xAct. So this really was an eye-opening experience for me, right? And then somehow I took on what he did and somehow tried to follow his philosophy. Okay, as I said, so this implementation of my book, right? So this is not complete, right? So and in fact probably it would never be a complete, so something that you could fully complete, right? But then I add on things that I require in the sort of in my upcoming and ongoing projects. So you have to load, as I said, xAct and TexAct, and then well, so as usual, so you define a four manifold, right, where you're going to work, and then for those of you who know the philosophy of working with conformal methods and conformal compactification a la Penrose, so the point is that you don't work on the physical manifold where you satisfy the Einstein equations, but rather in a conformally compactified version, right? And the notation is that the physical spacetime carries on some tildes, or every quantity associated to the physical manifold carries tildes, while those on the unphysical spacetime, which is obtained by the conformal compactification, doesn't contain the tildes, right? So then you define then you also define the metric on the physical manifold, right, which carries a tilde, as you can see here. And also there are a lot of checks. And then it turns out that besides this, you can also obtain some generalizations of these conformal field equations that actually are not associated to Levi-Civita connections. So there are more general structure called a Backdahl connection. So it's a connection which is torsion-free, but not necessarily metric. And you can also do this sort of consider this sort of connections or covariant derivatives in xAct, right? So it turns out that really, so xAct already has built in all these ideas to study conformal transformations, right? And then what is nice, and this is what I somehow learned from Alfonso, is that you don't type in the equation that you want, but then really you start very basic with your conformal transformation, right, between the physical metric satisfying the Einstein equation and the physical one, and then you go step by step deriving everything, right? So in particular, so you compute the transformation between covariant derivatives, right, from scratch, right? So then this gives you a setting which is completely self-consistent, where you don't have to worry from borrowing pieces of equations from different origins, or where there may be some clashes of notation or conventions, right? And then you go on, and then using standard tricks, right? For so you can do this as you were doing this by hand, step by step, derive somehow the transition tensor, right, that connects the two connections, right? So it's given in terms of derivatives of the conformal factor. And then you go on. So once you have this transformation rule for between connection, then you can also compute a transformation between the curvature, right? So this is somehow essential in this program of conformal field equations. So xAct has already built in, given two connections, tells you somehow the formula that tells you how to connect the two curvature tensors. Well, in terms of transition tensor, but then what it doesn't know is actually the actual value between the transition tensor, right? Which we already have computed, and then you go on, so you can specialize the transformation formula for the Ricci tensor, right? And then also for the Ricci scalar, right? So I think what is beautiful from this is that so you can actually do this almost as if you were doing the calculation by hand on your notebook, right? So this to say that, right, that if you don't know how to do the calculation by hand, right, on paper, you will not be able to do that, right? So, directly in the computer, right? So it's really the xAct really is really the tool here to make the calculation efficient, right, and to make sure that reduce the amount of mistakes that you can possibly do. And then again, as I mentioned, so some version of these conformal equations require these five connections, and then again, there is a transition tensor, right, between some physical connection, covariant Levi-Civita connection, and the Backdahl connection. This can be also again derived from scratch, so using somehow standard techniques, right? And then you go on, and then you can compute somehow. So the more complicated relation between the curvature of a Backdahl connection and the curvature tensor, right, of a Levi-Civita on physical metric. So on. And then so there are other objects, so the xTensor and so on. This is probably not so important for the discussion, right? But there are some other associated objects. Then again, so something that plays a role in the discussion are obviously the Bianchi identities, right? So there are relations that are used recurrently, and then you can actually derive them from scratch, right? So that and I think this is also something very, I think very nice, right? And somehow consistent with this philosophy of having a self-consistent world, right? That you are operating. Okay. So this is somehow, you see, there are a number of so this section is really about deriving somehow the basic relations, and then I guess somehow what is key is, well, so you can also derive the key equations that are used in my book, so namely these conformal field equations, and then somehow the most simple vanilla version of those are the so-called metric conformal field equations, and then again, so this notebook gives you a derivation of the equations, right? So these equations start from the transformation rule from the xTensor. So it's basically a trace reverse version of, or trace modified version of the Riemann tensor, which somehow naturally appears in conformal geometry. And then starting from that transformation, then there are a number of steps where it allows you to rewrite this equation somehow, the transformation as somehow a conformal equation, right? And then this allows you to identify certain new quantities that have to be defined, and that you define on as you go, and then you have obtained nicely the first equation, right? Which is somehow the only, is basically the transformation rule between for the Ricci tensor somehow in this guise, and then so on. So then you can construct all the other equations. For example, what we call the second conformal field equation is a sort of integrability condition from this equation. And then what you do, so you take covariant derivative, you do commutation. So you, because the covariant derivative equation, you commute, and all this operation, right, of commuting covariant derivatives and so on, substituting definitions that are done by xAct very nicely, and then you are having now the second equation. And then so on, right? So you do the other equation, right, which involves the Bianchi identities, right? So, and this gives you an equation for the xTensor, and so on, and then so on. Okay. So again, I guess what I want to show to you, right? So is that really, so once you have done this and you have derived your basic equations, then well, you are sure that they are correct, right? So and then you are self-consistent, and then you can go and do more complicated things, like for example compute. So it turns out that from this equation that I have shown you, you can actually derive wave equations for the basic fields, and then this is something that already involves more heavy computational calculation, where you somehow have to commute, apply covariant derivatives, commute many times, and so on, and then this can be done in a very clean and effective way here, right? So, let me just close this bit, and then just because I'm somehow short time and don't want to bore you, so I think that the other bit, I think that is crucial here, and xAct does it beautifully, is the following: is that it turns out that when you are trying to have a project with these conformal field equations, in fact, you don't use this basic formulation of the conformal field equations. I think I will not go into the reasons for this, but in fact, you need like a pepper up or power up version of those, and one of these versions that people use or we use is to have a spinorial expression, right? And then so for this, so one uses this package spinors, and then also SymManipulator, and then so what you can take, so again, so you can define the spin structure on your manifold, right? So this is something that is somehow built into spinors, and then well, so there, so you can again check all your conventions and so on. But so if you start from your basic to the equation, say like the first conformal field equation that I showed before, then there are a number of instructions, right, that allows you to transform this equation in a very clean way to its spinorial form. And then once you have it in this form, then you have well, all the powerful tools that spinors allows you to do, in particular making use of reducible decompositions and yeah. So and then this is done really cleanly without having to write type in the equation, right? And then you can do this in yes, as I said, by hand in a very clean way. And just I think what I would like to show you is say the last one, so which is somehow the most famous one, is the Bianchi equation, right? So given this rescale Val tensor, right, which is one of the key variables in this setting, so you cannot use this all the packages in xAct to obtain the spinorial version, right, which is written into the counterpart of D, which is a symmetric spinor. And just I guess as a last example, so it's well known somehow in the literature, although quite cumbersome, that from this equation it is possible to derive a wave equation for this symmetric spinor phi, right? And then, well, this is also again something that demonstrates the power of xAct. So if you try to do this in by hand, well, it's a calculation that you can do, right? But then in xAct, right, it's just a number of steps here, right? 10 steps, right? And then you obtain beautifully this wave equation for the Val spinor, right, in a very clean way. Okay. As I said, so I think at the core somehow somehow this shows the philosophy, right, that I was trying to explain to you, right, of trying to codify the book, right, that I showed to you. And then, of course, as I see, the point is that so this notebook here now, if you have a particular project that you want to undertake, right, so you can take the question from here, right, and take it from there. Okay. And maybe see if there is something else that I would like to say. Well, I mean, I guess I'm running out of time, but I just say that something that is also very important is that you like to do, say, given this conformal field equation, so you can also do a 3+1 decomposition, right? And then this is also something that you can do with quite conveniently, efficiently in xAct, right? So there is a whole section on how to do this, and there is also, I guess, for the more experts in spinor, so there is also say spinorial version of the 3+1 decomposition that we call the space spinor formulation, right? And then so again, so the beauty of this is that because of you have everything integrated in the notebook, so you can make use, so translate between formulations very, very easily, and yes, and translate and use information, right, from different approaches in a very convenient way, right? So yes, I think if you really have a very big project, say like this one, right, where you have several formulations of certain of your favorite equations, I think this is really the way to go, right? So yes, I guess, as I said, just to conclude, right? So I think I wish I had done that before I had written my book, right? Maybe it had taken me some time, taking longer to finish the book, of course, right? Because on and on, right? So this notebook that I'm showing here, it took several years, right, of work, right? So I guess that's just what I want to say, that there is an obvious investment in time, right, to prepare the notebook, but then once you have it, it really pays off. Okay, so I think this is what I wanted to say. So thank you for your attention, right? And well, I don't know if there are any questions. Probably there are some questions.
Thank you very much, Juan. That was very interesting. Yes, let's give a few minutes for people to ask questions. So a question that I think I'm going to ask all of you is, what do you miss the most in xAct? So what if you had to ask for something to be added, what would it be?
So I have to say that since I actually haven't worked quite a lot in this notebook in a number of years, right? But now somehow I recently have started a very large project as well. Because it's still in progress, I will not say very much, right? Where I actually have to do more development of xAct, right? So here I think I was more an advanced user, and then I have realized that actually a lot of the things that I would like to do are actually already done. But then I have discovered this really going very deep into the documentation, right? I think it would be actually great to have a more, some more extensive documentation of all the things all the commands that one can have, right? But probably this is very boring. But I have actually discovered, right, that many of the things that I may want to do are already there, right? And either you spend a lot of time and you find it already very deep in the documentation, or I ask you or Alfonso or Thomas that may know, right? But then sometimes one is not really aware of this, and I think this is probably one of the main challenges, right? That it's now, so that xAct is so big now, right? That sometimes it's hard to have an overview, right, of this.
Yep.
Yeah. So I guess this would be more like the request, I would say. Right?
Okay. Fair enough.
In a sense, right?
Yep.
Yeah.
Yes. Yes. Having better documentation is always a good thing. And for example, in the forum, we see that there are some questions that are repeated periodically. So that means that area requires better documentation.
I think, okay, so there's some questions there. So that is, I think, for Thomas mostly. Yes.
Okay.
Yeah, I mean, I guess just to conclude, I used to say that I wish I actually have learned this before, right? So I had as I said, the fortune of having interacting quite a lot for extended periods with Alfonso and Thomas. And then when they left, there was a vacuum in my life. So then I was really forced to learn, right? Yeah.
Okay.
So it does take time, right? But yeah, it's quite good.
Yes,
and
it makes you learn Wolfram Language too, which is also a very good investment.
Yes, that's also true. Yes, that's also true. Yeah.
Okay, thank you very much again, Juan.
Well, thank you very much.
I really appreciate it.
It's a pleasure.
And so now we will move to Cyril Pitrou's talk on Clifford algebra and trace techniques.
So what I wanted to say is that people know me in xAct or xTensor for this package. I've worked with a long time ago when Martin-Garcia was still in France, and it's called xSpan. And I will just talk about it like a few seconds, and then I will mention my talk. And this precisely is working as Juan Valiente mentioned before. It's using conformal transformation to compute the perturbation around Minkowski, and then promoting them as perturbation in cosmology precisely using conformal transformation. So really, it's just to say that this possibility of doing easily conformal transformation is xAct is really powerful, because that's how it's possible to do easily perturbations in xAct. So what I wanted to talk about today is not about this work where I'm very familiar, but it's something I'm really not familiar with, and which is among the xAct example notebooks. So maybe Jose didn't mention, but in the documentation here, if you go there, you see there is check out the great collection of contributed xAct example notebooks, and I think it's a great collection of several notebooks to give you ideas of what you can do, to give you ideas of what you can do with xAct. And among these notebooks, there is one notebook that now I'm going to go through and detail you, which is about Clifford algebra. And the very reason why I wanted to talk about this notebook is precisely because this is one of the area where I was the most surprised to see that xAct would help. And so I'm used to use xAct with general relativity, manifolds, covariant derivatives, all these sort of things, conformal transformation, Ricci curvature, Riemann curvature. But here, I will show you that you can use it to manipulate Clifford algebra in a way which is very different from what you can have from the spinner package. So the spinner package, the previous speaker mentioned it and showed you how it works. You can see the soldering form, and you can see explicitly the indices of the algebra, so which are the indices of the fiber, of the spin fiber. Here, I will show you that with the help of many people who work in xAct, we've been able to deal with Clifford algebra in a index independent way. So it's very strange the decision I took today to talk about that, because precisely the power of xAct usually is to show you the indices. You know, usually the mathematicians, they use this notation where you don't see the indices of the objects, of the tensors, and so on. But what we want to do in physics, we want to have indices such that we know what we're talking about. But here, I will show you that even if xAct was designed to show you the indices, it can still be used to do some very powerful and interesting computation in an index-free notation. So this notebook was done with the help of Leo Stein, who did most of the work for the Clifford algebra. And then I've stolen some input by Jose Maria Martin-Garcia, who helped me a lot. So there is a typo here, it's R. And there is also some inputs from Alfonso Garcia-Parrado, who's going to talk about various things today. And even I've stolen some methods by my colleague Guillaume Faye, who's going to talk about a few other things today. So the idea is that, I'll go through the package rapidly. The idea is that you define a manifold, but we're not going to use the full power of xAct, of this position-dependent manifold with covariant derivative and so on. We're just going to use the tangent space at a given point in space-time, and we're going to do some manipulation just at this given point of space-time. I have in mind that we're going to work in 4 dimensions, because what we want to do is Clifford algebra for particle physics, for instance. So I define the dimension to be 4, but not with an equal, such that I can change the dimension sometimes. But even if the notebook works for more general dimensions, I will show you and explain just things, how it works in dimension 4. So I define a metric, which is flat, because I have in mind that I want to work in Minkowski and do particle physics. And I will use of course, Minkowski signature with -1. So the first tool, which is interesting in xAct, is that you can define a product. You see the options of define product. There are many things which are complicated, at least for me it's complicated. The idea is that you first define an identity, okay? Define it, it's an identity inside as a tensor, but with no index, because it's there on the manifold, but it's just a scalar. And then you define an abstract product with in the xAct, which is with def product, which we call AP for algebra product. So this is what Leo Stein did in his notebook. And you said that it's a graded product, so it's going to give you an algebra and all these things. And then you define a tensor, gamma, which they are going to be the gamma matrices, the gamma Dirac matrices. It's going to be the Clifford algebra. And you say that the grade of the tensor is 1. And that's to say that essentially to say that what we're going to specify is not the commutator, but the anti-commutator of the gamma matrices. And we said that it's a complex. That is, there is a dagger. There's a notion of dagger of this matrix. And that we're not going to specify the spinorial index like we do in a spinor package. We're just going to work with gamma I. We're going to do products of gamma I, so that's why we have defined this product. We're going to do traces, and that's going to be my third part. And the second part, we're going to also to do irreducible decomposition of these products. So the first part, I will show you how to define products of gamma matrices. Second part, how to do irreducible decomposition. And finally, how to do traces. And that's basically all what we need when we want to do particle physics. So for instance, in this algebra product, we have a commutator. So you see that when I define it, it's like that. When I do expand commutator, it's the usual commutator. I have the anti-commutator, and I have the super commutator, which is the anti-commutator. So now, of course, I need to help xAct and tell it, that some things are part of the algebra and some things are just scalars. So I'm saying that when there is a plus, you have to look at if it's an algebra element on each of the terms. You have to say that it's a scalar, then you can, factorize it out and things like that. So for instance, you see, if I do the algebra product of 5 times gamma times 2 times identity times gamma, with these definitions, the factor 10 is going to go in front, and I'm just going to have this algebra product of gamma ij, gamma I. At this stage, if I use two canonicals, for instance, here I have the algebra product of one gamma matrix with another, nothing happens because I didn't tell xAct what to do with this product. It's gamma I, gamma ij, and so be it, gamma I, gamma ij, or gamma ij, gamma I. If I do two canonical, it stays in that order. So of course, we didn't tell anything about the algebra. So you see, again, if I put 3 products of gamma matrices and I do two canonical, nothing happens. But still, even when nothing happens, you can check the Jacobi identity. Okay, so the first thing you can do is you have to define what is the algebra structure. So that's the part which I took from Leo-Stein. So the algebra structure, you say that basically you build this rule that the anti-commutator of gamma I, gamma ij is 2 times the metric times the identity in this space of algebra product. And by saying that, now we're going to really specify what is the algebra structure. So here it's just an equality, and I'm going to use that to define a rule. So here with commute algebra rule, and using this algebra structure, then I'm able to create this rule, which is that whenever you have gamma I, gamma ij, then you can replace it by minus gamma ij, gamma I plus twice the metric. And now this is a very basic usage of this algebra product, because now there is a low-cost canonicalization that we can do, is that whenever we have a product of gamma matrices, we can reorder them with, let's say, for instance, increasing order of indices. Say we define that the order, if they are in alphabetic order. So you see here, I'm defining what is a disordered product. It's disordered if the indices are disordered. And then I can say that, okay, see, for instance, this is checking that gamma I, gamma ij is disordered, because when I read from the right to the left, I have ji, and it's going to be ordered if it's in order ij. So this one is disordered and this one is ordered. And now the low-cost canonicalization is just sorting these things by putting, whenever it's in the wrong order, I'm going to use the algebra structure, so the anti-commutator, to put them in the correct order. So this is what it's doing. Sort Clifford algebra product is putting everything in order using the algebra structure. So for instance, you see if you have gamma I, gamma ij, of course, it's going to stay gamma I, gamma ij. But if you have gamma j, gamma I, then it's using the algebra structure to sort it in the correct order at the price, of course, of having the metric appearing here. And just with this very, very basic rules, you can already check many simple usual identities. So for instance, of course, you can check that what is the commutator of gamma I, gamma ij, it's using the anti-commutator to find an expression, and this is what you get. You can check what is the anti-commutator. Of course, it's just to check that the rule that you've put in your system is there. So that's the rule we've put, and we recover the rule we've put. But then you can check what is the product of two gamma matrices. If you contract, for instance, the spacetime index, gamma A times gamma minus A. It means that there is a contraction, an implied contraction with a metric. And just, separating the metric, forcing the structures, forcing the product here, and then using the rule, and you can find that then it's equal to, of course, the dimensions times the identity. And so we can build a rule to say that from that we can build a rule that whenever we have the product of two matrices which are contracted, then we replace this by identity. And this is very powerful because the way xAct, so here there's a subtlety, and you see that xAct is really clever in the way it's designed. For instance, now I have the product of gamma A, gamma B, gamma minus A. So if I sort the product, it's going to be gamma A, gamma minus A, gamma B. So like the second line. But then this rule of replacement, which apparently is only for a product of two gamma matrices, can be applied inside the product, even though the product is a product of three matrices. So this replacement, the replacement of this rule is very clever, because even if it's not written that there is a product of two gamma matrices, because it's inside a product head, then xAct knows that it has to consider that any subpart of this product can be seen as a product on which this rule will apply. And so that's why it's working. And in the end, you get the simplification and you get the result. So this is super powerful. You can see you can have product of 4 gamma matrices. You contract there is a contracted index, which is simplified once you have put things in the correct order, and then it goes on and goes on. Okay, the next thing you can do when you want to do particle physics is that you want to define what is gamma 5. Gamma 5, if you know what is the dimension, is just the anti-symmetrized product of gamma matrices. So basically, it's the Levi-Civita with all the indices contracted with the gamma matrices with as many gamma matrices as dimensions. Here, there is a subtlety. If you do that, then the normalization of gamma hat is not what you want. You have to put some I factor or -1 factor. Okay, so I'm not going to enter to the details, but the way to deal with that is that you can enlarge your algebra structure, and instead of having just the gamma matrices, then you can have the gamma matrices, and the gamma 5 matrix. So now you have to specify 3 commutators: gamma gamma that we have already specified, gamma 5, and gamma 5 gamma 5. And this is what I'm doing here. I'm saying that they anti-commute gamma and gamma 5, and that gamma 5 roughly the anti-commutator is going to give you something proportional to identity. So here is the structure. You can see gamma matrices, the anti-commutator gives the metric, gamma and gamma 5 gives 0, and gamma 5 square gives something related to identity. And then you can do, and then you can say that you can force the rule that gamma 5 square is proportional to identity, such that you have automatic simplifications. For instance, if you have a product of gamma 5, gamma, you want the gamma 5 square to be removed. And this is what is done here. Okay, so the second part of my talk now, I'm going to talk about irreducible decompositions. So this part was taken from a notebook, which was called gamma.m. I can't remember where I found it. It was written apparently by Olaf Gran, and there is some inputs. I found I found a notebook from Alfonso, Garcia-Parrado, and Jose, who gave this notebook to me, and I adapted it to apply it to this algebra product, which was defined by Lowenstein. So the idea is that now, instead of having gamma matrices which has one index, which is tensor valued matrix, now it can have several indices. But in these several indices, it has to be fully antisymmetric. So for instance, you would have gamma I, okay, which is one index, so it's obviously antisymmetric. But then we can have gamma ij, for instance, or gamma pq, which is antisymmetric in its 2 indices. And then again with 3 indices, 4 indices, and as many indices as you want. And these are an irreducible basis for this algebra. So it means that at some point, what you want to do when you have a product of gamma matrices, you want to be able to decompose it as a sum of products of completely anti-symmetrized gamma matrices. Okay, here these are some subtleties about the gamma 5, which I don't want to enter. But then what this is doing? So I'm going to show you the results. So this is a very complicated algorithm. And I don't know how it works because I took it from this gamma.m. At some point, I knew how it worked, but then I forgot. So you can see that, well, it's not obvious how it works. It's quite complicated. There is a recursion, and there is okay. So it's quite complicated how it works. We even had some debate about some typo, because here you see there is I written that I've put a correction. So I think we had some debate with Jose and Alfonso, and we agreed at some point on what to put such that it works. And so then you can check that it works. So for instance, let's see how it works, because that's what we want to do. So for instance, if you have the algebra product of 2 gamma matrices being antisymmetrized times 2 other gamma matrices being antisymmetrized, and then you know what is the irreducible decomposition, then you apply the previous command, which is completely automatic. You get a decomposition in terms of things which are proportional to identity, or gamma matrices with 2 indices antisymmetrized, or a gamma 5 matrix. Okay, and you can even do, for instance, if you have a product of 4 gamma matrices, then you can have it as a decomposition of something proportional to identity, something proportional to gamma matrices with 2 indices, gamma matrices with 4 indices, which are then replaced in terms of gamma 5. And of course, you can check that it works. For instance, if you have something which is fully antisymmetric, and you expand it in terms of its gamma, like that, and if you do the gamma decomposition, you recover what you have put to you. Of course, you have to check that it works. And again, with 3 indices, if you decompose what this means, it means the complete antisymmetrization of gamma matrices. And if you ask what is the gamma decomposition, of course, it recovers that it's a fully antisymmetric gamma matrix with 3 indices. So this is very powerful. So these are some subtlety with the gamma 5. I'm not going to talk about that. Okay, so this is so that's the first part you can do when you have this algebra. You have product of gamma matrices. In order to have a unique way to write it, you want to be able to decompose it with this irreducible decomposition. Another thing you want to do when you do particle physics is that you want to do traces of gamma matrices. And so what I've done in this notebook is that I've defined a formal trace. Yes, I've defined a formal trace of a gamma product. So what I call spinor trace is the head, and that's why I'm using this feature of xAct, which is def inert head. So I'm defining the abstract, because since I have not put indices in my gamma matrices, I've hidden the algebra structure. Then of course I cannot do a trace like I would do with the spinor package by contracting spinor indices. So I need to use an abstract trace, and to put this abstract trace, I'm using this inert head, which is an abstract trace. So this abstract trace has to be linear. It has to, when you have the sum, it's the sum of the trace, or there are a few rules. And for instance, you can see how it works. For instance, if you have a tensor, for instance, if I have a tensor which is V, if I contract V with my gamma matrix and I put this abstract head, then you can see that I have the trace which is only on the gamma matrix, because for the algebra structure, V is just a scalar. So the trace of gamma I Vi is just the trace of gamma I times Vi. So this is just formal. I'm just telling how to put a trace on an expression such that the trace is only on the gamma matrices, on the product of gamma matrices. For instance, here you see I have Vi Vj times identity, and the trace is only on the identity. Now there is a very complicated part which I think I took from Jose again. This part, it's about how to compute the traces. The first thing you can do is that once you have the trace of a given number of gamma matrices, you can define a tensor which is by definition the trace of a given number of gamma matrices. And this time it has no algebra structure because it's a trace. So it has to be just a purely spacetime tensor. But it has some symmetries because the trace has some symmetries and the gamma matrices have some structure. And so with the help of Jose, at some point we had found that the group is quite complicated, but it's we had found what was a symmetry group of a product of gamma matrices. So I'm going to define TRN as the trace of n gamma matrices, and I'm going to force what is a symmetry group of this tensor. So I still don't know what is the trace of a given product of gamma matrices, but at least I know the symmetry group, and this already means that I can make some simplification. So see, these are, for instance, the groups which we build for the trace of a few gamma matrices. So these are complicated groups. And now, knowing what is this group, for instance, if you have the trace of gamma I, gamma B, gamma C, gamma D, plus the trace of gamma B, gamma C, gamma D, gamma A, just knowing what is the structure of this symmetry group, then ToCanonical is able to work on it, because these are just space-time tensor, and that's what xTensor is doing, is simplifying tensors, knowing what is the symmetry group of the indices. Of course, if I do that, I still don't know what is the trace, but I can simplify traces. So for instance, if I have a trace of 3 gamma matrices, just from the symmetry group, I know it's 0. If I have a trace of 4 gamma matrices, well, it's the trace of 4 gamma matrices. But I still need to know, I still need to compute what is this trace. And that's where the Guillaume Faye enters. So the Guillaume Faye was going to give a talk a bit later. He explained me something which is very interesting, is how to compute things which are quite time-consuming recursively, and to store the results of this recursion such that you only compute them once. So we're going to implement essentially this kind of sorry, it's a bit further. Yes, this kind of recursion. So we're going to use that we know the trace of n indices in terms of the trace of n minus 2 indices. Basically, that's the idea. So we have a recursive algorithm, so which is a recursive algorithm to compute the trace of n indices in terms of trace of n minus 2 indices. But if we don't store the values in the meantime, we're going to lose a lot of time. We're going to waste time. So what Guillaume Faye showed me is how to wrap this in some function which I call compute gamma traces, and which is going to store the values as down values. So here, of course, it's very complicated. I took it from Guillaume Faye, but the only important part that you need to know is this down values. You see, it's computing the traces recursively from the recursive formula. But once it computes a new value, these new values are stored in down values of compute gamma traces, such that it's only computed once and for all. So for instance, you see how it works. Computing the trace, the first time it computes a trace, okay, takes some time to get a result. For instance, this is the famous trace of 4 gamma matrices with A, B, C, D. You get GG minus GG plus GG, the usual result. Then once you ask it again, it will be immediate because it's already stored as a result. Okay, so this is to show you how to compute traces. And here, this is a wrapping function such that, you have a product You apply formally the head saying, I want the spinor trace, and then you compute the trace. See, for instance, I have a product of 4 gamma matrices. I apply the spinor trace formally, and then I compute the trace, and I get a result, which is, of course, it's just some product of gamma matrices, some product of matrix, some product of matrix, or some Levi-Civita, because that's all we have on the spacetime. Now, and before finishing, just 1 minute, I'll just show you. I've applied this to complicated problems of particle physics. I'm just going to show you on a very basic problem how it works. For instance, you have a process with 1 plus 3, particle 1 and 3 give particle 2 and 4. And you know that at some point you're going to use the momentum P1, P2, P3, P4 of these particles. They have a given mass. So, for instance, you put the rule that P contracted gives you the mass square. You define the famous slash notation. You know, when you have a P contracted with gamma, you know, it's going to be P slash. It means a P mu times gamma mu. And then you will have, when you do the computation of, I don't know, S matrix or M transitions and probability of from one particle to another, or reaction probabilities, at some point you will have some traces of product of gamma matrices. So at some point you will have some algebra product of gamma matrices. You put formally a spinor trace, you compute the trace, and you get the result. For instance, if I have this operator, which is slash P, so it means P times P slash gamma, plus times slash P2, plus the mass 1 times slash P2, something which happens due to Feynman rules. Then you do the gamma decompositions. Then you have two methods to find the results. Either you do gamma decomposition and you read visually what is the structure. So, for instance, this operator with this gamma decomposition, I can see that there is things which are proportional to identity, things which are proportional to gamma, and things which are proportional to the antisymmetric product of gamma I, gamma ij. I could have other products with gamma 5, but here I don't have things with gamma 5. So from this, I can read the various coefficients. The other methods, and I'm going to finish on that, is to multiply by the operator on which you want to know what is the coefficient and take the trace. For instance, I want to know in this operator, what do I have in front of the identity? Then I multiply by identity. I take the trace, so I put the trace, compute trace, and I get the coefficient with some normalization. I want to know what's in front of the gamma matrix. I multiply by the gamma matrix. I take the trace, and I get a result. Then I want to show that there is nothing which is gamma times gamma 5. I multiply by gamma and gamma 5, take the trace, compute the trace, and I get 0, meaning in my operator, if I was to do the irreducible decomposition, there would be no gamma mu, gamma 5. And this goes on, and then I've applied it to Compton collision, Klein-Nishina formula, all these things, and that's why it was very useful for me, because I wanted to keep the spin. I didn't want to sum on the initial spins and the final spins of the particles. So I had something which is more general than what you could find in the particle physics books. And so for this, xAct was very powerful and very helpful. So just the fact that you can hide the spinor space, but still have it there through this algebra product, I found it very powerful. So I'm going to find that. Thanks.
Thank you very much, Cyril. That was very interesting. And it was a good example of how xAct can be used in an area for which it wasn't prepared to.
Yes.
Yes. So
that's why I showed it, because it's really not what I do usually, but I was really surprised to see that it could be used for particle physics as well.
Yep. And you mentioned the use of products, which is one of these things that, as Juan was saying before, is not perhaps as well documented as it should be. So these products are like general algebraic operations, and you can have all sorts of symmetries and anticommutativity, and yeah, you can have Lie brackets, things like that. So it's any general product operation. So you can have rings implemented, for example, using a couple of those products and things like that. Okay. Yes. So let's see. Is there any question about this? So there is a question right now about, or a suggestion about introducing automated irreducible decompositions of tensors into spin parity states. To be honest, I don't even know what that is. So if somebody else here knows, I recommend to reply to that. Yeah, so something we haven't shown is the forum. So that could be good to show here. So this is the xAct forum, and so this is a Google forum. This is the place where most of the questions go. I see also questions about xAct in Mathematical Stack Exchange or even in Wolfram community, but this is the canonical place to ask questions. And so you see we have more than 1,000 threads already. And yep, so if you don't know whether xAct can support some type of computation, or you would like to make a suggestion or something like that, I think this is a good place to post, and we will try to address your question or suggestion. Okay.
Jose,
Yep,
you asked the previous speaker if he had some suggestion about how to improve xAct.
Oh yes, of course. Go ahead. Do you have?
Yeah, there was one we discussed, is that the integration between xTensor and xCoba. So when you do formal computations with xTensor, and at some point you want to replace by values in a given chart, and then you need to cheat with the metric, because since you have defined a metric with xTensor, and you have this def C metric in xCoba, and you need to like cheat and replace the abstract metric of xTensor by this metric component, by this component metric of xCoba. And this is the part I've seen in the forum, because you mentioned the forum, where people didn't know how to go from abstract to transition from xTensor to xCoba. So the answer usually that I give in this forum is that to do brute force replacement, but it's a bit it looks like a hack.
Yes. I think yes. Actually, yes. So there was a very recent question a few days ago about that, and yes. So let me share again. And yes, I know what you mean, and I agree. It's something that should be easier to do. So I'm going to share again. Share screen. So yeah. So this is the notebook that we shared recently. I'm going to put it bigger. And effectively, this is the function to do. So this code contains this function, which takes a symbolic matrix defined with def metric, and then a C metric, which is a xTensor object. And then this function is the one that will be able to get let's see if I can run this quickly.
Okay.
This is yeah, so this is computing everything about the metric or curvature tensors. And then at the very end, we have this type of computation. So we had something here, which was this thing, a purely symbolic object. And then we replace that symbolic metric by the C metric. So metric is a xTensor object. So we can put here minus A minus B, and we see the metric. And then there are some additional. So because this was perturbation theory, there was also a replacement of a perturbation by the corresponding tensor and a scalar field by a function of coordinates. And so in the end, you get that thing, right? Which is a two tensor with those components. So yeah, so I think what we should do is essentially to have this function in the system so that we don't have to copy it again and again. But yes, you have a good point. Yes, so now we will have Alfonso Garcia-Parrado, and he will talk about calculus in vector bundles using xAct and its applications to Young-Mills theory.
Okay, right. So, well, this presentation has two parts that you can see now in your screen. Well, before just explaining each of these two parts, well, let me just mention that I have been using xAct for for almost all of my career, and I found it I have found it very useful. And okay, if you are interested in doing involved tensor analysis computations, I think xAct is definitely for you. And one of the parts of the system that I find very important is the part of the system that deals with vector bundles, because this is the kernel for example, the Spinor calculus package that has already appeared in Juan's talk, and also it can be used to implement, for example, Young-Mills equations. So what I'm going to do is, well, this talk is divided into two parts. In the first part, I will just review the implementation of vector bundles in xAct. And then in the second part, as an application, I will illustrate how the Young-Mills equations with no matter content can be implemented in xAct. Okay, so right. So let me just start. Well, I start here by reminding the mathematical definition of a vector bundle. We have a number of ingredients. We have the base manifold. We have the bundle manifold, and we have the projection of the bundle manifold on the base manifold. And then we have the so-called standard fiber, which in this case, since we are dealing with a vector bundle, it turns out that the standard fiber is a vector space. So as people, well, as those of you who have worked with vector bundles know, then this is basically mean that we have manifold that is split into disjoint sets that are the fibers, and these fibers are vector spaces. Okay, so let me just illustrate how this structure is implemented in xAct. Well, I need some preliminary code that I will be using. So okay, so we start by defining a dimension of sorry, we start by defining a manifold of symbolic dimensions. So I need to start defining first the symbol that will represent the dimension, and then we define the manifold itself. Okay, so where are the ingredients of well, this definition defines automatically the most basic vector bundle, that is the tangent bundle of manifold. So if we check the list of vector bundles that we have now, we have we have just the tangent bundle of our manifold. Well, just to show you here how this is this symbol is represented. And okay, so we can check that all the ingredients of the definition of vector bundle are here for this specific bundle. So we have the base manifold of this bundle is the manifold M that we have defined. The dimension of the vector bundle is the dimension of the vector space fibers. This in this case, it coincides with the dimension of the manifold, and we can the fact that this is a vector bundle implies that we can attach a list of abstract indices to it. Okay, so in this case, these are, well, I'm going to use Greek indices for as the abstract indices for the tangent bundle. So well, if I just go back for a second to the definition of the manifold, well, you can check that. Well, I said that vector bundle is automatically defined, and as the argument you are given the dimension, and you are we are given the list of abstract indices that we are going to use. Okay, so definition of a manifold gives us automatically all the ingredients to define the tangent bundle. But as you know, that if we want to do tensor analysis, we need, in addition to the tangent bundle, we need the dual of the tangent bundle. And then by doing tensor products of these bundles, we get the so-called tensor bundle. Well, one of the powers of this abstract index notation is that we don't need to define a new vector band, a new we don't need to define any of these tensor bundles, because these definitions are implicit in the list of abstract indices. And also, well, if we in physics, in addition to a manifold, we need a metric. Or in other words, suppose that our manifold is a space-time manifold, so we need to define a metric. And well, the metric automatically defines all the structures that you need. Well, the def command. Well, you can choose to see this, whether you are going to see these structures by means of the def command, or you can just check these commands that tell you exactly what is automatically being defined when you define the metric. Okay, so we have well, the classic structure, the classic space-time structure, and right. So now let us define what is the topic of this presentation. Let us now define a vector bundle that is going to have the manifold M as its base manifold. But now what is going to be different is the standard fiber. So I'm going to define a standard fiber that is going to, well, I'm going to define a vector bundle whose standard fiber is going to be a vector space of dimension n. So first I define the symbol that will represent the dimension, and then I use xAct command to define the vector bundle. That is the vector bundle. And okay, so we can check that all the ingredients that are needed for the definition of a vector bundle are present. So we have the vector bundle itself, the vector bundle manifold, the base of the vector bundle. We have the dimension of the standard fiber, and also we have the list of abstract indices that as I said, well, this is the mark or the token that tells us that this is a vector bundle, that this is well, and also, as I mentioned, this abstract index notation saves us the work of defining all the tensor products of the vector bundles that we need to do tensor analysis. Right now that we have the vector bundle, we want to do calculus in the vector bundle, and for that we need a linear connection in that. Well, it can be defined as a bilinear operator that takes sections that takes sections of the tangent bundle and 10 sections of the bundle itself, and returns a new section of the bundle. Okay, well, this is the mathematical definition. Okay, well, there are some extra conditions that I'm not detailing for lack of time, but everyone who is well, who is familiar with differential geometry knows. Then okay, so I define the covariant derivative, and again a number of additional structures are defined that I summarize here. Okay, now I want to stress two of these different well, so, actually, some of these different structures. On one hand, we have the Christoffel tensor of this covariant derivative that, well, is the usual space-time Christoffel tensor. And then, since this is a covariant derivative that has been defined in a vector bundle, we have what we call, or what is called the A Christoffel tensor. And okay, this, well, the Christoffel tensor is, well, Christoffel, well, okay, in xAct, connection components are tensors, and the way in which that's achieved is that they are always defined with respect to a reference covariant derivative. In this case, if if nothing is set, by default we use the reference, the PD, which is a partial derivative with respect to a generic coordinate chart. So we have the Christoffel symbols, that is the usual Christoffel tensor with all its space-time indices, and we have also the what we might call the A Christoffel tensor, or internal Christoffel internal connection components, and here we have one space-time index and then two vector bundle indices. So we have two sets of connection components, and something similar happens with the curvature. We have two curvatures, the standard Riemann tensor, and then the vector bundle F curvature that we call F Riemann tensor. And you see, okay, Riemann tensor has the usual structure with all its space-time indices, and F Riemann has two antisymmetric indices, and then it has two bundle indices. Okay, so right, so these are the definitions. And okay, so there are you can, as I said, you can do calculus with all these quant objects. And now I start with the second part of the talk, that is how this can be applied to a Yang-Mills theory. Well, for doing that, let me just remind you the background, the mathematical background of a Yang-Mills theory. And okay, the first point is that Yang-Mills theory in modern, well, in the modern approach is formulated not in a vector bundle but in a principal bundle. So we have again a manifold and something which is the principal bundle, and we have the bundle projection. And now, rather than standard fiber as before, what we have is a Lie group. And okay, the situation is that we have G is a compact Lie group, that is going to be the gauge group, and G small g is its Lie algebra. Then we have we define a connection in what is the gauge connection in the principal bundle P, and it can be shown that this connection is represented by one form, that is a gauge a Lie algebra valued one form, and the curvature of the connection is given by this equation. And just in terms of this of the curvature of this connection, you can write down, you can obtain the Yang-Mills equation when you don't have any matter content, by means of this expression, where capital D is the exterior covariant derivative that is defined from the gauge connection, and star is the Hodge dual defined using the metric G. Well, okay, now in xAct, in xAct there is no implementation yet of principal bundles, but it turns out that for any representation of the Lie group on a vector space, we can define an associated vector bundle with base manifold M and standard fiber, the vector space V that we use for the representation. So what we can do if we want to implement Young-Mills equations in xAct, we can just work with the associated vector bundle, and that is what I'm going to do next. Okay, since I have already defined a vector bundle, I'm going to use this vector bundle as to the associated vector bundle of some principal bundle in which a gauge connection has been defined. So what I need to do now is define a covariant derivative that is going to represent it's going to be the covariant derivative associated to the gauge connection that we have in the principal bundle. And okay, in this case, it has to be a covariant derivative that when acting on space-time tensors, it coincides with the usual Levi-Civita covariant derivative that we define along with the metric. Okay, so this is what basically this command tells us. Now I need to introduce a product that is going to represent the Lie bracket or that we need for the Lie algebra. And as Cyril already explained how this works, and I need to specify the constants of this product, and also this is going to be the correspondence between the connection one form that we have in the principal bundle and some field that is going to be defined in the associated vector bundle. So we are going to have a field, the so-called gauge potential in the vector bundle, and we are going to have the so-called field strength that corresponds to the curvature 2 form that we have in the vector bundle. Okay, so the Lie bracket works as expected. So that means that the gauge potential and the field strength are tensors, but are now are tensors with values are tensor are Lie algebra valued tensor fields. So it means that we can multiply them with the Lie bracket, and the canonicalizer knows the properties of the Lie bracket, right? So now I define the Lie group generators, the Lie group, the Lie algebra structure constants that are constants with respect to any covariant derivative, and of course they are scalars with respect to the Lie bracket product. And I just can write down the standard commutation relation of the Lie group generators. And also we have the Jacobi identity that we can the Jacobi identity translates into some properties of the structure constants that you can deduce doing computations. Okay, I'm not detailing too much these computations just for lack of time, but I think that anyone who is familiar with these things will recognize what exactly I am doing. And with these ingredients, I can define the components of the gauge field or the gauge potential in the Lie algebra basis that are now scalars with respect to the Lie algebra. So we get the standard expansion of the gauge potential in terms of the Lie algebra generators. Okay, and so we can just expand the Lie bracket, and there's something similar for the field strength, which again is a scalar, and also I have the expansion of the field strength in terms of the components of the field strength in terms of the Lie algebra generators. Right now we have the ingredients that we need to obtain well, there's something that, else that I have to do, and is since since we want to write down the Young-Mills equation in some generic coordinate system, I need to introduce a generic basis in the vector bundle. This is done in this way. So this generic basis, or okay, you can think of this as a frame in the vector bundle. Is well, it's the Lie bracket of this generic frame is given by this expression, and okay, I can express Lie algebra generators in terms of the frame, and the coefficients of the expansion are precisely the structure constants. And okay, we can check that this is consistent with the Jacobi identity that was obtained before. I'm not detailing this computation just by lack of time, but I think that people familiar with this sort of computations should understand what I am doing, at least in a general vision. So right, so now I have I really have I really have the ingredients. I define now the coupling constant and the covariant derivative that is compatible with the general frame. So meaning that the covariant derivative of the frame is 0. This is going to be an automatic rule, and the components of the connection and curvature are regarded as scalars with respect to the algebra product. Now, any covariant derivative, any gauge covariant derivative can be expressed in terms of the covariant derivative that is compatible with the general frame. And I can now set up the relation between the internal Christoffel symbols that we have in the vector bundle theory and the gauge potential that comes from the principal bundle theory. And this is the relation, and something similar for the field strength. I can set up the relation between the field strength and the components of the curvature of the gauge connection that we have defined in the principal bundle. So okay, then it gives me just obtain an expression of an expression. Well, I'm just going to run the computation and explain at the end what this expression is. Well, this expression is again the relation between the field strength and the gauge potential that is that can be found in every textbook. And okay, this is the expression that can be also written in terms of the gauge covariant derivative, that covariant derivative that is compatible with the metric. Okay, this formula is obtained assuming that we are working in a frame, in a vector bundled frame, such that its space-time part is holonomic, is a coordinate frame. Okay, so now with this expression, I can just take this expression and where is it? Yes, it's here. Okay, I've thought it. Okay, so I can just take this expression and write down the Young-Mills equation. Okay, so I just have to replace what I got in the previous slide and run the computation. And okay, here it is. Here, okay, you have the Young-Mills vacuum equation fully expanded out in terms of the structure constants of the Lie group, the metric tensor, the gauge potential that you define in your vector bundle, and here you have the Christoffel symbols that you would get from your space-time background. For example, if you want to write down Yang-Mills vacuum equation in a Schwarzschild background, then you compute these Christoffel symbols, and then you could obtain this set of equations. Now, you could either give an ansatz to the gauge potential, that this is one of the things that is usually done, or you could try to solve this equation as a partial differential equation, just by trying to find a hyperbolization of this of the equation. Okay, I think that my time is out, so I will stop here, and thank you for your attention.
Thank you very much, Alfonso. This was very interesting and a very nice introduction to vector bundles. Indeed, a very important part of how xTensor and all of xAct works. Okay, so we have a minute for some questions. Let me remind you of the polls about messages. So I see some votes there, but I would like to see more. So you saw, for example, in the presentation by Alfonso, how the def commands produce all these messages reporting all that has been created in real time. Again, there are ways of quieting those messages, but I see many people quieting them by default. So I wonder whether we should actually have them quiet by default. Alfonso, the same question I posed to everybody. Anything you would like to see added to xAct?
Okay, I think this the implementation of principal bundles would be interesting, because that would allow us to give the other formulation of gauge theory that I reviewed. Also, related to this, I think that the interaction between wedge product and this Lie bracket product, I mean, when you are in a session where in which you have several different products, like here, if I want to just write down the gauge equation, the Yang-Mills equation in a principal bundle, I need to work with wedge product, with Lie bracket product, and eventually with tensor product. So one has there at least 3 products, and this I think that Canonicalizer needs a bit more of training for that kind of situation.
Okay, so let's move on, and now let's have the presentation by Thomas Backdahl. He's going to be talking about 4 packages he has created: SymManipulator, SymSpin, SpinFrames, and TexAct.
So, thank you for the introduction. I'm going to talk, just briefly about these packages, and I've written, parts of all of these. SymManipulator, I've written all by myself, the other ones with collaborators. So just to load the packages, we have the standard way of loading, and SymSpin loads all of them. So just to save some time, I'm loading it like that. And then, as we just mentioned, we don't want all messages about creating everything, just some sign convention and specifying some 4-dimensional manifold and a metric, just so we can start doing things. So the SymManipulator package, what happened with my screen? Sorry. The SymManipulator package it was designed to handle abstract tensors that have been symmetrized. So, for instance, if we take a balance for a tensor here, which happens to be symmetric in the last two indices, and then impose a new impose symmetrization on the last three, we can display it just as a single object like that. And we can, of course, expand the entire symmetry. But then if we canonicalize, we see, oh, we only need three terms to express this due to the symmetry, built-in symmetry. And in fact, if you just give expand sim an extra option, we only get these three terms. So it can do the expansion in a bit more clever way. And this expand sim S is just a shorthand for the same thing. So the way this is stored internally is that instead of having just one tensor head, we have this compound object, a SymH object containing the tensor head, the imposed symmetry, and a label. And then it's actually treated by xTensor as just an xTensor object with a specific symmetry operator, with a specific index symmetry. And this index symmetry is computed from the both the internal symmetry and the imposed symmetry. And this is the largest symmetry group of monoterm symmetries that you get. In principle, one could get multi-term symmetries, but at the moment, xAct cannot really handle multi-term symmetries in a good way. But we'll see ways around that shortly. So what can we do with this? So, for instance, if we look at a Maxwell field and a potential, then we can write a relation in this way. So just this antisymmetrized version of the derivative, but we can expand it again, of course. And then we end up with a problem that, let's say that we have some complicated expression with several terms of derivatives of A and want to turn them into F. Then here in principle, we would need to turn two terms into one. And that is in general a fairly bad idea to do in computer algebra. So instead, we can do the following trick, that we split up the derivative into a symmetric and an antisymmetric part. And here we use the SymManipulator package to handle these parts. If we just expand this, we see that it's true. And then we see can replace this antisymmetric piece with F. So if we get some bit more complicated expression where we want to transform these derivatives of A into F, we can just use this decomposition and canonicalize the result, and we get what we want here. So this is how you can work with tensors. But the problem, well, one problem which has been alluded in some of the questions here is that in general, if you have more indices, this decomposition we made here into symmetric and antisymmetric part, this becomes much more complicated and requires Young tableaus and quite a lot of complicated representation theory. And not very much of this has been implemented in xAct at the moment. There are some basic things in extras, for instance. But a different way of handling this is to use spinners, and for that I've implemented some sort of irreducible decomposition. So first we just define some spin structure and set up a nice display form of certain things. So here we just define a 3-index spinner T, and then we can do decomposition of this into a symmetric part, this last part here, and then some antisymmetric pieces. But in spinners, because the spin metric is of 2 complex dimensions and it's antisymmetric, this also means that all antisymmetrizations can be turned into traces. So we get different pieces here, and all pieces are always symmetrized traces of the original spinner. And if you have different valences, they will always be independent. But unfortunately, not all of these pieces are really independent, and therefore I try to fix this. Instead of doing proper representation theory, I actually just fixed this by implementing this function in the PRD compose that looks for possible dependent spinners and finds relations between them and uses that. So in the end, you can eliminate one of these things. So if we go back to our Maxwell case and just translate them to spinners, we can do it like this. And then, well, A is already irreducible, but F is not. So if we can do just this simple decomposition. And here we see that we get a symmetric piece, so we can name this phi. We can define it like this, and then the other piece actually happens to be the complex conjugate of that. And here the symmetrization is not strictly needed due to an interplay between the antisymmetry and the trace, but still, formally this is what we have. And then we can use this to get a very nice decomposition of F into phi and the spin metric. So then if we look at the relation between F and A, we can translate this to spinner language. And here we already saw how we can decompose F, but now we also need to decompose the derivatives. And in general, this can be done. And we have these fundamental spinner operators for that. And just to explain what they are, I just define some other spinner with higher valence. So this symmetric valence 2, 3. So 3 unprimed and 2 primed indices. We can do this with a long definition, or we have a shorthand version with just symmetric spinner with valence 3, 2. So what these fundamental derivatives are is divergence, which means you contract both indices. We have the curl, where you contract a primed index and symmetrize over the unprimed, and curl dagger, where you contract the unprimed and symmetrize over the primed, and a twist where you just symmetrize the indices. So then we end up with symmetric spinners again. So if we do this for our relation between F and and A, we end up with just this relation between, so phi is minus curl of A. And we also have the complex conjugate of that. But in general, in spinorial equations, we don't need to write out the complex conjugation of equations. So let's say now that we want to handle a wave operator on A, then we could use inert head, for instance, but that would mean that we would act on A with its indices. But we can actually do something like this to define a wave operator that acts directly on any tensor or spinor, and the result is something with the same number of indices of the same kind, with the same symmetries. And for instance, we can define it like this for our particular case. And we can decompose this into the irreducible, the fundamental spinor operators. So we get a nice simple equation. But now when we have all of these operators, we see that, well, we actually don't really need the indices any longer because we have no dummy indices. We only have free indices, and all the spinors we are dealing with are completely symmetric. So that's why I implemented this SymSpin package, which can handle this. We have seen that derivatives of symmetric spinors, we can use these fundamental operators on. But then we also need products of symmetric spinors. But these can also be decomposed into symmetrized traces. And therefore, I defined this SymMult operator that defines a product. So in this case, it's phi CD, which is the Ricci spinor, trace-free Ricci spinor, contracted with this T32 as we defined above here. This just means that we contract two unprimed and one primed index and then symmetrize the result like this. The sub-indices here are just the valence numbers to keep track on that. You can turn that off if you like. But now, as I said, we don't really need the indices. Then we can take just index-free form of the same equation. And here, this minus sign is now implemented as a multiplication with some scalar, and in this case it's just a constant. It is so we can keep the result as xTensors, so we can put indices on them, etc. So if we take our wave equation, for instance, here, we can just make it index-free like this, and then it's very easy to do commutators on this. All of these commutators between the fundamental operators are implemented, and they work even if you have 5 or 6 of these operators acting on each other. And then we can here just replace this curl of A with minus phi as we had earlier. So we can do this even when this is quite deep within the equation here. And then we see here that the sum here is represented through a new tensor plus rather than a plus, just to keep it as xTensor objects. But if we want, we can just go back to ordinary index versions with very quick step 2. Something which you cannot do with the index form is defining symmetric spinors with valence numbers that are symbols. So this we can do. So we can actually take these derivative as operators on something of valence KL, and we can even do commutators here. So this would be quite cumbersome to write out with indices, but it can be handled very quickly. So let's see. Now, very quickly to the SpinFrames package here. In this package, we implement the Newman-Penrose and Garcia-Penrose formalisms. So, and we have had the spinor formulation in mind when we did this, even though that's not absolutely necessary. But we just need to define a tetrad and the corresponding spin diode. And then we can take, for instance, binorial form of the Maxwell equation, and then turn it into Newman-Penrose formalism. But here we are keeping all the free indices, and therefore we get all of these tetrad components. But then we can just pick out the different, the diode components, and we can just pick out the different equations from that. We can, of course, also do the GHP formalism, which I actually prefer for almost everything. A quite nice thing is that we can even take this index-free form of it, and then we can do this much quicker. Because here we don't need to, we don't have any floating free indices to deal with, and we don't need all these components. The diode. Anyway, so just to see, I'm not going to say very much about TexAct, but just a little bit. So, for instance, if we have these Sigma H objects, they work really well with TexAct if it's possible to write them out in the standard way. If you have very complicated things which is impossible to write out, then it's going to print it as some sort of Sigma H object instead. Something you always can do in TexAct is you can define a new tech form of whatever object you want. For instance, here, if I want to change the potential here to maybe a macro or something, slash potential A, then I can do that. But I don't want that right now, so I'm changing it back. Then, of course, we sometimes get long equations like this long equation we had here. Then we have two functions, TexPrint aligned equations and TexPrint aligned expressions, which automatically line breaks and aligns the equations. So you see you have line breaks here. And these are not just estimated, it's actually every term is sent to LaTeX to check the width of them, so you can compute the proper line breaking you need. But for this to work properly, you need to set up your class and packages and all other definitions you need in your tex file for this to work properly. And you can even use TexView to directly see what an expression looks like in tex form. Usually that is displayed externally in your PDF viewer, but you can also turn it on to use to import it back into Mathematica, but then it's using a different class code here, which you can set up whatever. So, for instance, here we had that long expression line broken. Unfortunately, here the resolution was not so high, so that's something I should fix. So you can set that as a parameter. I found out what to do about that. So you can also add sub-equations and things like that, and then you have your Maxwell equations in a simple way. Something I quite often do is then use copy to clipboard, because then it's very easy to clip it into your actual article. So I suppose I'm almost running out of time here, but I just wanted to show that the SpinFrame package is also quite useful when you're doing more complicated calculations. So, for instance, here I have a general background, which is just a general manifold. A general metric, but it's a vacuum. And then we get the Ricci relations, and I just want to reorder them a little bit. And we have the Bianchi equations. I just want to solve for certain derivatives. And then what I want is this following expression. And I want to prove that this is true. I have derived this using these tools, but it's easier to prove that it's true. And these are nonlinear versions of the Tucholsky master equations. And here I've even used this inert scalar OP, which is just same thing as function, but with a nicer display thing, so that you can have this factored form of operators. So if we take this and just expand the inert scalar OP, and then we can use the Bianchi and vacuum rules. We can do commutators. We can do Bianchi and vacuum rules again, another commutator, and finally the Bianchi and vacuum rules, and then we see that it's true. So you actually don't even have to think about, oh, this term we need to do that or whatever. You just hit it with these rules as many times as you want, and then you end up with this, and then you can print your result if you like. So I think that is what I intended to say.
Thank you very much, Thomas. That was very nice. Yeah, TexAct is very powerful in them producing LaTeX results for all these expressions, and I'm amazed with how many symbols you use in your equations. So you really take advantage of the power of typesetting in Mathematica.
Yeah, and the less you have to do after you have produced your equations, the better, because when you start doing manual edits of your equations, then that's where you start to introduce errors.
Absolutely.
I find that quite a lot. So that's why I've spent quite a lot of time also on improving the TexAct to produce human readable codes that are as good as you can make them, basically.
Yes. Yep. Yeah, and there is the freedom of typesetting any tensor or any object as you like, and controlling line breaking and many other things. Yeah, it's a powerful system. Okay, very good. So let's see if there are questions. While other people ask, my question to all of you: what do you think is the most important thing to add?
this thing I mentioned here, if you don't go over to spinners as I've done, then if you handle more complicated expressions, you do need this sort of irreducible decomposition also on the tensor side. And that is something that we're really lacking. This requires young tableaus and well, some representation theory, which I need to read up on before I could possibly implement this. And of course, I would need a lot of time to, and some help by people who knows that well. But otherwise, I think that with that one could handle, for instance, like the Bianchi relations also in tensor language, and in some sense also multi-term symmetries in fair generality by doing this sort of irreducible decompositions, but on the tensor side. But in spinners, I think what I presented here, these tools are enough to get around that problem. So at the moment, one can translate things to spinners and then perhaps back if one wants to, but in the end, it would be good to have something purely on the tensor side.
I fully agree. Okay. Yeah, so then let's move on to our next speaker, Guillaume Faye. He's going to talk about post-Newtonian calculations with xAct and xTensor.
So I am very pleased to be here to celebrate the 20-year anniversary of the first xAct release. And I'm going to show how to do post-Newtonian calculations with this tool, xAct xTensor, which is something that people want to do very often. I have not designed any public package because I use my own formalism. It's very specific and it's always changing. There are new quantities to add and so on, but I can tell about the main ideas. They are very simple, nothing very complicated, and I use basic tools of xAct xTensor, but they are very powerful. So, okay, it's 7. I should not exceed 20 minutes. I will try to do that. So let us first initialize the session and load xAct xTensor. I will need a few constants, like Newton's constant, and the speed of light, the space dimension, and a small parameter, because actually I'm going to talk about post-Minkowskian expansion, which is perturbative expansion in G, Newton's constant, and post-Newtonian expansion, which is perturbative expansion in 1/c, the speed of light. So now I can describe the geometric environment. Here I define my manifold first. So my computer today is a bit old, so I hope it will be enough. So here is the space-time manifold with Greek indices in d+1 dimension. I have flat metric eta associated with the derivative, which is a generic partial derivative. So I can evaluate that. It's done already. So I do the same for the space manifold with Latin indices. I have a time parameter, and I, of course, define a flat metric delta with also the partial derivative. And for instance, this is the metric, and of course, it does not depend on time. So let us move on and go to the gravitational field, which is regarded as a tensor field on the manifold endowed with a flat metric. I have only my partial derivative that is compatible with the metric, so I can put this parameter to false. And now two canonical recognize that the metric commutes with the partial derivative, and two partial derivatives commute. So no problem about that. Everything is flat. I introduced the Gothic metric notation. I have my perturbation, which is the deviation of the Gothic metric from the flat metric. It's also useful to have the usual metric perturbation, the stress energy tensor, whatever you need to do general relativity. And then I do the same definitions in d dimensions for just the space part. Also, the determinant is needed in d dimensions. I have some simplified notation for multi-time derivatives, as you can see here, because there are a lot of them. Okay, so now here is the relation between the Gothic metric and the perturbation h mu nu. This is our perturbation. Using the small parameter, I introduce a truncation command. For instance, here I truncate the square root of 1 plus h squared at order 10 in h. You see, so it works. Sorry, I was too fast. So here, this is the post-Minkowskian order. I need to execute this piece also. And here, something quite important, it appears to help a lot in long calculations to eliminate dollar indices that appear explicitly in the index rules that are generated automatically. So I will have this command to do that. I have then the relations between the quantity I am interested in, the quantities, and h mu nu. And for instance, here I show the relation between the metric perturbation and h mu nu, just to show how it looks like. It depends on the space dimension d, of course. This is now the stress energy, pseudo stress energy tensor of Landau-Lifshitz, okay, in terms of the inverse metric, the Gothic metric, and so on. The left-hand side of Einstein equation is written in terms of the derivative of the third superpotential. So I define this superpotential here. Then combining those two things, I have the Einstein equations saying that this is equal to 0, this thing here. And now I use my rules to replace everything in terms of h, and I truncate at every step. And here is the final result. So the Einstein equations are there. But I need to consider most generally the right-hand side of the equations and inharmonic gauge. So here I define some rule for the gauge condition. Here I apply it to check it works. So you can see that here is an index on the derivative contracted with an index is h mu nu. And so I apply this rule and I truncate on my right-hand side of the equation. This is not yet the right-hand side. I need to remove the piece which belongs to the left-hand side, and then I obtain this tau mu nu tensor, which represents the right-hand side of Einstein equation in with some stress energy tensor T mu nu in terms of h, okay, the h perturbation. Very good. It's useful sometimes to remove T mu nu from this if we are outside the matter system. This object is of course symmetric, as you can check easily, and you can extract the quadratic part. For instance, this is the quartic part because you remember at some point I said that my order was 4. Okay, so I stopped at quartic order, but if I had slightly more time, I could show you easily to go to order 6. Here you have 31 terms in this quartic part of the source. Sometimes it's useful to unsymmetrize something which is symmetric. So I have a very simple command to do that. This means that when you have defined this unsymmetrized quantity, if you resymmetrize it, you will come back to the original quantity. And the gain is that you have less terms, and if you need complicated manipulations, this is useful. Now, of course, at the end, we want to do post-Newtonian calculation or multipolar expansions. So we need 3+1 splitting. So I define a time manifold. I need some rules saying how my tensor are noted in d dimension, space dimensions. So they are generated automatically for the tensors of interest. And then I use those rules in this simple code based on very simple and basic xTensor command. So for instance, up index or some pattern here, indices of, get indices of V bundle, trace dummy, which is very important here to trace on indices. Okay. So now I show an example. So I apply this command. Here I say that mu nu become just time indices. So this is the 0, 0 component. And I simplify a bit with this combination of two canonical put scalar and contract metric. I obtain this. This simplification can be defined in some arrange command. And here is an example on the 0i component. Very similar result, but with less parentheses, scalar parentheses. Okay. And finally, the ij component of the source. So it takes slightly more time, but it's still very short. Here you have 341 components. So I think my computer is a bit ill tonight, so it goes very slowly. Okay, so if I unsymmetrize it, I get less components, and then I can do further manipulations. I will focus later on the quadratic contribution. So I define the quadratic part of the source and move to the next section. So I am setting the space dimension to 3. And now I'm interested in multiple moments. So multiple moments parameterize the linear metric. So here is the mass type moment here. This is symmetric and trace free. Similarly, I can define a current type moment. I define some radial variables, some other useful quantities. I mean, it's not very interesting. The angular part will be described by a vector, unit vector, depending on theta and phi of the spherical coordinates, pointing towards the field point. And actually, this vector can be multiplied with itself, a tensor product, to obtain a tensor of length of rank L involving n times the unit vector, and we call this NL with some multi-index. So this is defined here. This is very convenient. So for instance, it's a symmetric quantity. You can combine two NL tensors with themselves. If you contract indices, they disappear because of the unit property of NL, which is originally just one vector, unit vector. I will need some generic index to specify what multiple moments I am interested in. So this means that I am interested in the quadruple, mass quadruple, and the current quadruple. I call them moment 1 and moment 2, and I will use this later. Now, of course, I need more properties. So the multiple moments are trace-free. You can compute their derivatives. They are retarded quantities. So if you compute the space derivative, you obtain some time derivative here. You can, of course, compute the derivative of the angular quantities. Now, I am in the position to start more serious things. So this is the general definition of a linear metric, but I truncate it at some order. Here it's 4. Okay. So I obtain the result explicitly at this order 4. This is 0, 0 component of H, 0 I component, and ij component. And I can check that the result obeys the vacuum Einstein equation, linearized. So the source is 0 here. We are in vacuum. Okay, so we expect to find 0, and the gauge conditions are satisfied. Okay, so because my computer is a bit slow, I think I will move on, even if it's not completely finished. Now it's done, I think. So now I will define some command that takes some quadratic expression and replaces there the metric by its expression in terms of the multiple moments, keeping only the 2 moments I have considered before, the current quadruple and the current and the mass quadruple. So here, for instance, in this particular source, there is no such interaction, but if I consider the square of this time derivative, the interaction is not non-zero. Okay, here I now can compute the source, and I can actually simplify it. The longest thing is the simplification. It takes a few seconds. So I think I will just show you the structure involving here it's a scalar. So you see that scalar are there everywhere. You have epsilon Levi-Civita, the angular part, the radial part, and multiple moments. And just the interaction I have considered. But because when you do post-Newtonian calculation, you know in advance what interaction will contribute to a given order. So here I do the same for the other components of the source. So I will go faster. So you see the structure is similar, but now they are not scalar anymore. And you do the same for the ij component. So without waiting for evaluation, you see it takes about 20 seconds for this one, for instance. But it may take a bit longer now due to the weakness of my computer. So I go to the next step, which consists in defining the symmetric trace-free part of this angular object NL I defined before. This is equivalent to spherical harmonics. I could as well use spherical harmonics, but because I use xTensor, I like to use the power of tensors. So here I define this object here, for instance, with 1 index. Okay, so it's still computing. Okay, I think I may skip further evaluation if it's so slow tonight. Yes. Anyway, so I can go on, I think. The outputs are visible. So here you see it's really a symmetric object, hopefully when it will evaluate. And it's trace-free. Here it will take 23 seconds, even more perhaps now, if I evaluate this symmetrized product of metric, which I need to relate the n hat notation to the n tensor I introduced before. So this is quite long. I will not execute that. I don't want that I am stuck. Instead, I have my own command that computes precisely the combination of deltas that are there in this particular symmetric combination. So I don't use symmetrize. Perhaps I could do it with SymManipulator, but here I don't even consider symmetries. I just generate the indices and I put them correctly in the way they appear in the formulae. And here it is very fast. Even with my slow computer, I generate this in a fraction of a second. And actually, I save the result in the command itself, which makes it even faster for further evaluation. Very good. So I can now define a command to transform. So here it's not very interesting, but to transform generally NL into its decomposition in STF quantities, STFN. I can do it in d dimensions, actually. So here are the formula in d dimensions. Okay, this is quite fast. And more explicitly without gamma functions here. Very good. Now I can do exactly the reverse and transform STF NL hat to decompose it in L and to write explicitly the expression. I will not show because it's a bit long. Here, if I use STF part, because it's not tuned to my specific notations and so on and symmetries, it will take 11 seconds while I have 2 less indices. For the equal number of indices, it will take quite a long time. So here, I can compare the 2 results. They are the same, but I will not do it due to the weakness of my computer. I come back to 3 dimensions. Now, I will quickly show you how to integrate these equations with xTensor. So actually, I want to apply box -1 operator. I need to define integrals, and in integrals, you need to say if you have an object like this, at what time, time being the integration parameter, you consider it. So those objects are constant, therefore, there is no need of argument. The dipole is 0 in our center mass frame, but if you consider quadrupoles, you can specify at which time you evaluate them and use them in some integral command. This integral does not evaluate anything. I mean, it's an inert integral defined with inert head that we discussed in earlier talks. So for instance, this is this inert integral applied to so this object, third derivative of the quadrupole, evaluated at this time, and time runs from 1 to infinity. It's not exactly time, it's almost time. And we have a log kernel. You can have constant objects in arguments. They go outside the arguments. Here, the angular dependence also goes outside. Okay, now I have also some commands to integrate using the box -1 operator and the tools I just introduced. I don't show the code. I have no time to do that. I just show how it works. So here it's very simple. Now you have some cutoff that appears. Another simple example, but here some integrals is generated and I need my integral notation. Okay, very good. I will skip this and go directly to the evaluation of this on my source. But first, I need to express my source in n hat, in terms of n hat, because the retarded command is defined only when you expand in spherical harmonics. So this is what I do here. So you see, it's similar compared to previous expressions, but now instead of n, I have n hat. I can apply this. Okay, I can print the result. Well, yeah, so it's a bit ugly. You have a lot of dollar indices, but it's computed. Okay. Yeah, it's quite long. Right, it was just to show you how bad it can be. If I apply to canonical, it doesn't work actually. I do it just for fun because why? Because in the integrals, here one of the integrals is written here. You have complicated sums multiplied by the kernel. And so to canonical does not like sums like this put all together in one inert head. So what you have to do here is to expand what can be expanded here, but keeping the kernel intact, because otherwise the integral will be divergent. And then you replace the sum of the kernel by a fake sum. So I need to evaluate this to define my fake sum. Then this simple rule, and the rule fixes the problem. Here, this is the fake sum. It's not very visible. I should maybe improve the notation. Then I define an integral arrange, and now I can simplify my expression and integrate the 0, 0 component. I will not do it due to lack of time for the other components, but it works equally well. I can show you quickly the 0i component here, and similarly the ij component. It starts to be slightly long, 500 terms. Okay, very good. So very quickly, I think I'm a bit too long perhaps, but I want to discuss the application of those ideas also to binary systems. So I reset my session because I'm going to load a package and there are notation incompatibilities. So I hope this time the loading the package will not make any problem. No, it seems to work. So this is a package based on xTensor I designed notably with Sylvain Marsat many years ago. Okay, now let us go to the tensorial environment. So the field point is represented with the radius r and some unit vector. Okay, the particle positions are y1, y2, the velocities v1, v2. So this is the configuration space. You have the separation vector y1 minus y2 split into angular and radial dependence, and similarly for the separation between the field point and the body point. So you see always angular part and radial part. So anyway, so those are the notations, and now I can define the stress energy tensor components, the parametrization of the stress energy tensor for point particles. I need to redefine the metric in 3D. The metric is parameterized with many potentials, and I can show you just for fun the expression of the metric at 3pn in terms of those potentials. But then those potentials need to be replaced by their actual values. So, and those values are quite ugly, actually. So the variables are what they are. So unit vectors are unit vectors. You can simplify scalar products using relations with radia. Now, let's go to the core of this. You can differentiate 1 over R1, for instance. Okay. Second derivative, the Laplacian of 1 over R is 0. This is a well-known property. You can do it on more complicated combinations involving the two bodies, y1 and y2. You can then use the command simplifying scalar products and arrange things a bit. You can do that on this logarithmic kernel, and the result can be further simplified with factor, and it's well known. So it's a very good check. You have time derivative. The 0 here just specifies the Newtonian, post-Newtonian order. Here, it does not play any role, but for the derivative of the velocity, you need to say that the acceleration is the Newtonian acceleration or the post-Newtonian acceleration or whatever. Here, this is the 3pn acceleration involving this number of terms, and then you can differentiate it 2 times. So I try to do it. And you will find that the number of terms here is 541 after simplification. Very good. It's also useful sometimes to have time differentiation without replacement of acceleration. Now I think I will skip volume integration, but I have commands performing 3D integration and regularizing the results. Instead, I will go directly to this part because I would like to show you some ideas about how to apply replacements. So I have complicated potentials, and to replace them, I design rules that depend on the post-Newtonian order. So there will be a rule for order 0, 1, 2, 3, and I truncate at each order. So the rules are already evaluated. They are not re-evaluated each time you apply them. This accelerates a lot the replacement process. But of course, the first time you evaluate this cell, it takes a bit. Yeah, I think I can go on. If you replace V by its value at Newtonian order, you find this very simple result. If you replace it at 3pn order, you will find, when the evaluation will arrive there, you will find something much longer. Let me still evaluate. And finally, if I replace by an order which is too high, which is not known yet, you find nothing special to avoid mistakes. Okay, so now I think maybe I have no time to evaluate anything in this section. I just want to show you some. Yeah, it's still running. It's very bad tonight. Huh? It's Friday night. So the mass here can be replaced by its value, okay, which is computed here in this cell from the potential. It takes a few seconds, but it's too slow tonight, so I will not try to do it now. Still computing this cell. It's terribly slow. And now here I did fantastic, wonderful. So I was not lying, as you can see. So I could compute this rule for mu1, and I find this mu1. Then I compute the source. These are the components of the stress energy tensor in the case of point particles. Mu tilde was just computed in terms of the potential. So now this is the source of the potential V. And therefore, you can integrate this source using the rule for mu. And I have a command to compute retarded integrals and truncate. And actually, I can recover the potential V because this source is precisely the source of potential V. So V was needed to compute this mu tilde in the source of V, but only at 2pn order. And here I computed V at 3pn order. When you proceed iteratively, you can compute at higher and higher order. So here I am not trying to evaluate it. It takes too long, and I think I am running out of time. But here you will find something with 1,000 terms. Not very long yet, but it starts to be a bit longer. It's still not exactly the same as the V that was loaded at the beginning of this session, but the difference can be computed, and this is just due to the fact that I neglected odd contributions in powers of 1 over c in the V I have loaded. So it just proves that I really recomputed something and not just computed the same thing. I mean, faked when computed it. Also, I could not launch actually evaluate the cells due to the slow state of my computer tonight. So a few words to end with about large expressions. So the R potential is a longer potential, but more complicated also. So if I replace R by its value, so it takes a very short time, so it's fine. If I expand the result, it's also reasonably fast, except tonight. But now if I use index rule for this replacement, it is much slower, yeah, especially now. You see 6 seconds, so it's 3 times slower than when I executed it this afternoon before. And if I try to expand this result, it takes this amount of time. I will not even try to do it
Right.
now.
So don't evaluate that one.
No. So now I use this change expand command that freezes all symbols of the expression. So this prevents xTensor to try to do things during the evaluation. And now the expansion takes a few seconds. It will be longer tonight, but it's still manageable. And another way to do the same would be to avoid screen dollar indices, but this is still longer than the previous solution. I will not even try to apply my derivative x because of the dollar indices appearing in this differentiation is quite long. It is shorter if you map the result. So I have a map derivative x command to do that actually. Then if I have a large source depending on my potentials, I can try to replace the potentials there. So for instance, this is the compact part, and I just showed you before the non-compact part of the source. The compact part means that this is the stress energy tensor. Okay.
Guillaume, we are running out of time.
Oh, okay, sorry. So finally, I can show you the result. So the result is that if I load this after replacement, I obtain something which is very large, and the evaluation of this with arrange with two canonical is very long. And so I think you have to be clever in this case, check that the metric does not appear in the expression, that the expression structure allows you to skip two canonical, and that you can use two canonical only on the scalar. So I think I will skip the rest and go to the main message of the talk. So for me, xAct xTensor offers all the tools for the state-of-the-art in perturbation theory and very high-order post-Newtonian theory and also post-Minkowskian theory. It is well adapted to manipulate multiple moments efficiently with higher number of indices. The basic xTensor commands allow to design more elaborate commands tuned to the considered problem. So it is better to really tune the commands to the problem. And I find that for very large expressions, two canonical contract metric are powerful, but should be used only when strictly necessary. And dollar indices, they create problems in rules, definition, and scalar. And so we should find ways to avoid them if possible. Sorry about that. My computer had a bit of problem, but I could go to the end finally.
Great. Thank you so much. This is a really difficult area, and I've always been amazed by the performance here. So we don't have time for questions, so let's go directly to... So thank you very much, Guillaume, and let's go to Barry.
So this is work that I started, I guess, near the start of when xAct was around, about 15, nearly, not quite 20 years ago, maybe 15 years ago. And then left it for several years, and then had just come back to it quite recently with Kevin Kiley, who's a PhD student in UCD, where I am, and also with my former PhD advisor, Adrian Otwell, and Jose has also been helping us with some of the things we've been doing more recently. So I'm going to talk about green functions and Hadamard expansions and how they relate to Riemann tensor canonicalization. I'll maybe just give people a little bit of an explanation of the first two parts here, the green functions and Hadamard expansions, and what I mean by them. So there are a few things that we need to set up before we start talking about green functions. So I'm going to define a few quantities and show how they generalize things that we're used to in most physics courses. So the first thing I'm going to introduce is this thing called the Singh world function. This is just a function which measures the distance between 2 points. So if you've got a point x and a point x primed up to a factor of 1/2, the world function sigma is the square of the distance between them. And in relativity, when we talk about distance between points, we need to define exactly how we measure that distance. And in the case of the world function, it's distance along the geodesic that connects the 2 points. If you take a derivative of this world function, well, it's a function of 2 points, of x and of x primed. So you can take a derivative with respect to x or with respect to x primed. What you get is a vector. So we usually denote the covariant derivative with a semicolon. Because we're going to encounter so many derivatives of sigma in these slides, we usually leave out the semicolon. And then anytime you see an index on a sigma, read that as covariant derivative of sigma. So that derivative is a vector, and it turns out that it is the vector which has length being the distance between x and x primed, and pointing oriented in direction from x primed to x. So I've denoted those vectors here by the blue arrows. This world function sigma satisfies a fairly simple equation that 2 times it is equal to the contraction of its derivative with itself. So sigma A is 2 sigma. Oops. Sorry, just need to move the thing out of the way there. And then, so you can think of these as equations, which also have initial conditions. And the initial conditions are that the distance between 2 points, when you bring the points together, is 0. And that the second derivative of the distance between the 2 points, as you take the limit of the points going together, is just what we mean by the metric. So that's the world function. It measures distance between points. Another thing we encounter in the calculations I'll talk about is something called the bivector of parallel transport. This takes a vector at a point x, here's the vector TA, and it parallel transports it along the geodesic from x to x primed, and allows you to define a vector at x primed just by contracting the first vector with this bivector of parallel transport, GA primed A. This bivector of parallel transport is defined through a transport equation. Its derivative, covariant derivative, projected along the direction along the geodesic is 0. In other words, it is parallel transported along the geodesic. Along with the initial conditions that when you bring the points together, this bivector of parallel transport is the metric. And then if you go back to the definition of what a geodesic is, that allows you to use the bivector of parallel transport to take a sigma vector at 1 point and up to a minus sign transport it to a second point. Okay, so the last thing I want to introduce, the last fundamental bipensor, is what's called the Van Vleck-Moret determinant. And this is a scalar which measures the focusing of neighboring geodesics. So if you have 2 points here, x and x primed, then the geodesics, two neighboring geodesics of x will either go parallel to each other, or they might converge, or they might diverge. And that's measured by this thing, sigma, which is the determinant of the matrix of second derivatives of sigma. And this Van Vleck determinant also satisfies a transport equation, which is that its derivative along the sigma direction, so the square root of it actually, this d prime just means take a covariant derivative and then project it along sigma, is equal to 1/4 4 minus the box of sigma times delta to the half. So you can think of this as an ordinary differential equation defining sigma along defining the Van Vleck determinant along a geodesic. Okay, so why is all that stuff useful? Well, what we're going to be doing is considering green functions, and we're going to be taking series approximations to green functions. These are going to be in curved spacetimes, so we need to have a generalization of the idea of a Taylor series, which we encounter all over the place, to the context of curved spacetime and relativity. So in flat space, well, what's the distance between 2 points? It's just the magnitude squared of the vector, of the difference between of the vector connecting the 2 points, x prime minus x. So and the derivative of sigma is a vector, which is the vector going from 1 point to the x prime minus x. So with sigma here, we can generalize the idea of a Taylor series, which is if you have a function a of x and x primed, then you can expand that function in a Taylor series where you've got a set of coefficients here, these a's without any with indices on them, times delta x's, or in our case, sigma a's, sigma alphas. So this is the generalization of the idea of a multi-dimensional Taylor series to the case where you want things written in a covariant way in terms of covariant quantity sigma. We can use a shorthand that each of these terms in the series, these a contracted with sigmas, is just a sub k. And then you've got the standard rules for infinite series that, well, the one at the bottom is very standard. If you multiply two infinite sums, then you can write that as a sum of products with a binomial factor in it. You can also differentiate these a series along the sigma direction, and that just has the effect of multiplying the kth order term by k. Okay, so that's kind of the mathematical machinery we need. Now, just to introduce the idea of a Green's function. These are things we encounter in physics all the time. We deal a lot with wave equations. Here's the scalar wave equation. Box of some scalar field phi is equal to minus 4 pi rho, where rho is the source. One way we can solve this equation is by using the Green's function. So if we have a Green's function, a fundamental solution to the equation given by box of the Green function, which is a function of 2 points now, is equal to minus 4 pi times the Dirac delta of x and x primed. If you can solve this equation for g, then you can find any solution for the scalar wave equation with any source you want by convolving with g. So a given solution phi of x is obtained by integrating g times the source over the full spacetime. Okay, so that's in flat space. Well, this is a general statement. In flat space, Green functions are easy to find. They basically just tell you how things propagate along null GD6 from one point to another, and null GD6 in flat space are straight lines. In curved spacetime, things are more complicated. Null GD6, or the light cone in curved spacetime, is complicated. For example, if you think about a Schwarzschild black hole, which would be kind of represented by the cylinder in the middle of this left diagram, then the light cone of some point here at the vertex in Schwarzschild spacetime has this very complicated self-intersecting kind of structure. So that's going to complicate the Green function in one sense. And on the right is the Kerr case, which makes it even more complicated. You add a bit of rotation into it. So this is just to say that the Green function in curved spacetime has quite a lot more structure to it, and it's more difficult to find than the flat space one. And that's largely, here's another plot of a similar thing. If you take a slice through one of those light cones and you plot the Green function, you can see that it has support not just on the kind of the light cone, which is the null GD6, but also everywhere else in the spacetime. So that doesn't preclude us from being able to try to compute the Green function. In fact, there's one very nice way to do it, which is that if the points x and x primed are close enough together, I won't define precisely what that means, but essentially if there's one GD6 connecting them, a unique GD6, then we can write it in this Hadamard form, where it's a combination of two pieces. There's this piece here, which the important bit you want to read out of here is that there's this delta of sigma. Sigma is 0 when the distance between 2 points is 0. In other words, when they're connected by a null GD6. So this delta function has non-zero support only on the light cone. So this represents propagation along null GD6 of the scalar field, for example. Now, because it's a curved spacetime, as things propagate along null GD6, if those GD6 are expanding or contracting, then you don't just get a 1 here like you would in flat space. So in flat space, we'd have delta to the half as 1, and you just have this delta, and you wouldn't have this second term at all. In curved spacetime, this delta to the half now captures the fact that as things propagate along GD6, it gets focused or defocused. Then the second part that's new in curved spacetime is this extra bit. This has a theta function, a step function, that has a minus sigma inside it. So it's only non-zero. The step function is only non-zero inside the past light cone. So the first bit's on the light cone and the second bit's inside the light cone. And again, there's another function here, I'm going to call it v, which is not yet determined. So we have this green function, this Hadamard form green function that seems nice, but we really just moved the problem onto figuring out how we're going to solve for delta to the half and v. Well, it turns out that there's a way you can do that using transport equations of the type we saw earlier on in the talk. So in fact, this v here, this term in front of the theta, you can write that formally as a series in sigma. So it's a sum of terms, vr times sigma to the power of r. So here the r here means raised to the power of rather than covariant derivative, just for clarity. So this is a power series in powers of sigma. And then you can write down, the nice thing about that is you can write down equations for these VRs, which are transport equations. They're ordinary differential equations along GD6. So the first term is given by the derivative along the GD6 of V naught plus an extra term involving V naught plus a term involving the box of the Van Dyck determinant is equal to 0. This is an ordinary differential equation, sorry, a transport equation for V naught. And likewise, you can write down similar transport equations for all the other terms in this Hadamard series. And these Hadamard coefficients turn out to be the thing that we really want to compute to be able to get the green function curve spacetime. And they're also closely related to what are called DeWitt coefficients and heat kernel expansions. Okay. So the question is then, how do we actually solve these transport equations for the V naught and VRs? Well, there's an old-fashioned way, or a traditional method, which is basically you start from this equation for sigma, the defining equation for sigma, you differentiate it a load of times, and then take the limit as the points go together. And if you need to go up to a certain order, say order sigma to the power of s, then you need to take 2r plus 1 plus s derivatives of sigma. And that sounds fine, but you can see here a scan I took of my former PhD advisor's work when he was working on this before I started my PhD, doing it all by hand. And I don't expect you to be able to read that, but the point here is that these are very long, complicated calculations, very prone to error, but very naturally applicable to computer algebra. So very, very, very rapidly becomes impractical to do these calculations by hand. And even using computer algebra, when I started working on this, I started using xAct to do this algorithm. And it sort of worked, but even then it was very inefficient. So the solution is that there's a better method. And that better method was published about just over 10 years ago now in this paper, where we wrote down a set of transport equations, and we were able to use that to directly solve for the V's rather than going through this kind of differentiating and taking limits approach. That paper came with a package called covariant series. It's a Mathematica package that computes these V's for you and gives them in terms of the Riemann tensor. In principle, that's great, but the problem is that the results you get are not necessarily in the simplest possible form. So this covariant series package will spit out an expression, but it's not simplified. And more precisely, it's not in a canonical form. So not only is it not small and compact and easy to put into a paper, it's also very difficult to check if it agrees with someone else's calculation of the same thing. So this is where xAct came in for the second time in this project. We used it to take the expressions that were generated by this covariant series package and canonicalize them. Now, xAct on its own does very well with canonicalization, but it only knows about single-term identities of the Riemann tensor, effectively. So any symmetries of the Riemann tensor that involve relating more than one term with another one, so 3 terms, for example, are not captured by the algorithms built into xAct. And unfortunately, the Riemann tensor actually has an additional symmetry, which is the Bianchi identity. And this is a term relating three Riemann tensors to each other. So on top of xAct, there is a package called invar, which is part of xAct, which basically, by essentially a brute force method, teaches xAct about the Bianchi identity. And it allows you to canonicalize things into the simplest possible form. So with that, I think I'll just switch over to Mathematica and actually give a demonstration of this covariant series package and how I use invar to simplify the results. Okay. Hopefully you can now see the Mathematica notebook, in which first thing I'm going to do is load the covariant series package. I will then load invar, and I'm going to define this rule, which is to do with the potential and the wave equation. I'm not going to worry about that. If we now go down and ask this covariant series package to compute V0, it will do it. It will spit it out in this specialized notation that we invented for this calculation. To make it more clear what this really means, we can convert it to what I call xTensor format. So this covariant series package hooks into xTensor in that it can generate xTensor expressions directly. So if we take that thing and convert it to an xTensor expression, we see that V0 is actually 1/2 the square of the mass plus or minus 1/12 essentially the Ricci tensor, Ricci scalar. Sorry. And we can simplify that to change the Riemann tensor into a Ricci scalar. Okay, so that's V0. It looks like there's nothing wrong yet. What about when we go to higher orders? Well, V1 is a bit more complicated. The expression in terms of Riemann tensors also becomes more complicated. And now you're starting to hopefully see that this is not the sort of thing I would want to do by hand. Fortunately, 2 canonical is enough to sort out most of the simplification. But let me hide these messages, not completely, and we see that if we use Riemann simplify, which is the invar command that also uses the Bianchi identity, it reduces this fairly simple expression into something even simpler. So the first part is that simplifies it, but it also, if I wanted to compare this against some existing calculation, I could subtract the 2, and only if I had Riemann simplify available would I know for sure that they agree with each other or not. And just for demonstration, we can go to one order higher where things get a bit more complicated. Generating the xTensor expression is quite painful. It doesn't even fit in the, we'll print it out by default. If we canonicalize it using 2 canonical, it at least gets it down to the point where it will print on my screen. But it's still not in the simplest possible form. And hopefully that shouldn't take too long. There we go. So the canonicalized version is this, but we have not yet applied the Bianchi identity. We're now going to apply the Bianchi identity and using Riemann simplify, and we'll see that we get an even simpler expression, which is in what's guaranteed to be a minimal canonical form. So simplest, in some sense, the simplest possible form. And I'll just get rid of the messages. You can see that it is indeed a shorter expression than the one above. Okay, so let me go back to the slides for a second, and because I don't want to spend the whole day waiting for my laptop to run the higher orders, I'm just going to take out of the paper we published this table, which lists how far we went. So I've just shown you V0, V1, and V2, and the covariant series code just generates 2 terms, 10 terms, and 91 terms for those things. Once we canonicalize using Riemann simplify, we see we get down to 2, 4, and 15. So the V0, it doesn't make any difference. It makes a bit of difference for V1, and it's starting to make a very significant difference for V2. So remember, each of these terms is a polynomial in the Riemann tensor. If you go to V3, you discover there are 1,058 terms, but actually only 68 of them are unique or independent. We also went up to V4, so we generated 13,972 Riemann tensor terms, but simplified them down to just 380. V5, we generated about 200,000 terms, and V6, we went up to about 3 million Riemann tensors. We weren't actually able to canonicalize them at the time, not because xAct couldn't do it, but because we didn't have enough RAM. This was 15 years ago. We should really revisit this calculation and fill in these two ones here. The table, the set on the right is where you canonicalize and you assume a vacuum spacetime where the Ricci tensor vanishes, so you get fewer terms again. And we were able to go a little bit higher order in that. But you can see that you're getting at least a factor of 100 improve simplification in the expressions. And we went up to V8 where there were 6 million Riemann tensor terms in the expression. So I guess showing the power of really pushing xAct to the limits. Okay, so I'm near the end now. What I've talked about so far, let me go back a second to when I introduced green functions. I was a bit sneaky here because I only showed the green function for the scalar wave equation, so where you've got a scalar field. The universe isn't made out of just scalars. In GR, in electromagnetism, we're interested in vectors, and in GR, we're interested in tensors typically. So you can write down equivalent equations for vector fields and for tensor fields. Good news is that the same ideas work in this case, but the bad news is that we now have free indices to worry about. And the problem this brought up was that INVAR, as it currently stands, does not know how to canonicalize Riemann tensor expressions where there are free indices. You can only do things which are scalars. So this was a bottleneck back when we initially did this. Fortunately, Kevin, the PhD student I mentioned, worked very hard on implementing a new package, which is coming soon to xAct. We have a kind of an internal version working at the moment. We have to polish it up and then release it quite soon, called tinvar, and it's basically an extension of invar to also be able to canonicalize Riemann tensor expressions with free indices. Okay, so let me do a quick demonstration of tinvar just to show you that it works in the same kind of way. So I'm going to do some setup here, loading. The most important thing is we're loading this new package, tinvar. Kevin also implemented a version of the covariance series package, which works with the vector wave equation rather than the scalar wave equation. So I'm going to load that in here. I'm not going to open it because it's quite long. And now let's go through the same thing we did in the scalar case, but now for the vector green function. So V0 now is something with two free indices. So how can you get that? Well, you can get either a Ricci tensor or a metric times a Ricci scalar. We can Riemann simplify that, and it doesn't change. So that one is doesn't really get much benefit. We could also, let me actually skip to the next one, V1. Now, it's going to take a little bit longer, but we can see that this has now generated a expression involving Ricci tensor squared and Riemann tensor squared. And then we can simplify that, Riemann simplify that, so canonicalize, including Bianchi identity, and get that down to a expression which is shorter. Now, rather than going on to V2, what I'll actually do is compute this thing V01, which is another, I don't have time to talk about what it is, but it's a off-diagonal parts of the V's. So the V's are defined in the coincidence limit. These are the off-diagonal parts. You don't take coincidence limit. Here's one where, again, we have a expression involving the Ricci tensor and Riemann tensor with free indices. We'd like to simplify that. So Riemann simplify will do the job nicely, and we'll get it down to something simpler. It's not much of a gain here, but as has been the case throughout, it's when you start to go to higher orders that things become more painful, and the gain of using Riemann simplify. Oops. Okay, I'm not sure why that's happening.
things
I
happen.
don't have, I won't diagnose that now, but suffice to say that this simplifies down quite a lot once you use Riemann simplify.
Mhm.
Okay, so I don't know how I'm doing on time, but I think I'm probably at the end of my time.
Yep.
So let me just leave up some concluding slides to say that green functions are a great way of solving problems involving the wave equation. Geometric methods based on bitensors are a good way to compute green functions, and the applications of all this stuff is quite wide, from quantum field theory and curved spacetime to cell-force models for binary black hole spirals. Okay, I'll leave it there.
Very good. Thank you very much. Well, thank you all for your talks. Very interesting. And just to finalize the event, I'm looking at the polls, and surprisingly, I was expecting that many of you would want all these messages removed, but it turns out you don't. There are more votes saying that we should keep them. So I think we will leave them there. So yeah, I'll close this one. So, okay, that's good to know. So thank you very much again, everybody, for attending today. We will process and post these videos so that if you want, you can watch them. And I think some of the presenters will share their notebooks. Other notebooks may not be shareable because they are like professional development notebooks. And yep, I don't think I have anything else to say other than thank you very much for your support of xAct. Keep using it. If you find any problem, please let us know. Use the forum. And yep, thank you very much again for being here today.